Hello and welcome to part 5 of the video series titled as Fundamentals of Reinforcement Learning. In the previous part 4 of this video series, we basically discussed the temporal difference learning update rules. And for that, we started with the returns and the expected returns. And we also saw how the temporal difference learning rules what kind of rules are there that define what update rule defines the SARSA algorithm, and what modification is there to define the Q-learning algorithm. And we end the last video with the temporal difference update rules for SARSA and Q-learning algorithms. In this part, we are going to explore this SARSA algorithm in detail, and we will also see how Q-learning algorithm is different from that. And we will write the whole algorithm step by step in this part, and in the next part we will be actually implementing Q-learning in NumPy on MapRover example. So let's dive in for SARSA algorithm step-by-step treatment of the algorithm. So the very first step is to initialize the state action value functions. You can initialize the functions to 0 or any value. I mean, the initialization might be small random values, or it may be 0. Further, the time where you start should set to be 0. So that's the initialization where the Q matrix is initialized and the timestamp is 0. So that's our initialization. Next, what we do is we pick some state at random. You can have picked the initial state maybe to be maybe S0 or maybe some beginning state if you have some ordering of the state. But I mean, in general, the initial state can be picked to be any random state. Again, at time 0, this can be picked the random state as an initial state. Now, this SARSA algorithm depends upon it's an on policy algorithm, so it depends upon the policy. So what we do is with respect to certain policy, let's say epsilon greedy policy, this should be epsilon here. Just for convenient, I write E. That's the epsilon greedy. It's a greedy which takes a greedy choice with a particular probability and non-greedy choice with the remaining probability. So if that's the policy, if E greedy is your policy or some other policy, you sample an action AT for state ST, and that's your sampled action AT at state ST. Obviously, when you take that action AT from ST, you will switch to another state ST plus 1, and by taking this action at ST, you observe a reward RT plus 1. So that's what you have observed. Now, you start from ST, you sample an action AT by some policy, and you then take that action from ST and you observe the reward RT plus 1, and this action leads to some other state which is ST plus 1. So that's what you did so far, step by step. Next, what you do is now, after taking action AT from ST, you observe the reward RT plus 1, and you are now in state ST plus 1. Now now the state ST plus 1, from this state, there might be several actions, A1, A2, A3. There might be several actions, and each action will lead to another state. So what you do is you have to pick an action from the state ST plus 1, but there are several choices, there are a lot of actions. So what you do is you sample an action AT plus 1 out of the given actions A1, A2, A3. There may be several actions. So you sample an action AT plus 1 of these actions according to some policy, let's say epsilon greedy policy, at ST plus 1. So again, you sample an action out of the given action from the state ST plus 1, and let's say that action is AT plus 1. That's your sampled action, and that sampled action at state st plus 1 will be chosen by some policy, some given policy. In this case, let's say E epsilon greedy policy or any other policy that you have fixed. Now, just to recap, you initialize your matrix, you initialize your state, the starting state, you sample an action using a policy, you take that action, observe a reward, and you are in a new state. In new state, you have your policy, so you sample an action at the new state, and that's the action AT plus 1. Now, once you have all these observations, now you actually update your state action pair function, and that update is basically the k plus 1 update, and that is basically the previous value. These are the previous values. So what you do is you apply a temporal difference learning update, where this is your target. This is your target. This RT plus 1 is your immediate reward. When you take an action AT at state ST, that's your immediate reward. This is the action AT plus 1 that you sampled according to some policy when you were in state ST plus 1. So given a policy, you can sample that action. So that is this action. So, and this Q ST plus 1 and AT plus 1 has some value, already some value. That's an estimate. So this RT plus 1 plus gamma Q ST plus 1 AT plus 1 is an estimate to the expected return that we discussed in the previous part of this video series. And this is again your original value that you're starting. That's a gap. This is the gap, and you compensate that gap by taking alpha steps towards decreasing that gap. So that is your iterative update for this particular case. So that's the iterative update. So everything is given here. Alpha might be, that's basically learning parameter, learning rate, sometimes called learning rate. It's a hyperparameter, and normally it is set to be, it should be smaller than 1, and it depends. If the alpha is very large, then you're taking very big steps, and if alpha is small, then you're taking very small steps. Intuitively, what should happen is in the start of the learning phase, the alpha might be large, close to 1. But so in the start, you'll be expecting to observe large gaps. So you have large alpha, but as you move your iterations, the alpha should progressively decrease. That's one way. The other way is to set the alpha as constant value throughout. So either way, that is your discount factor, gamma. And the higher discount factor, if gamma is very close to 1, that means you're weighting much more. You are sometimes called the far-sighted in future. And if the gamma is very, very small value, then you're not accounting for the future returns very much sitting on a particular state. So as you move in future with small gamma, the returns that are very far away are less contributing. So that is the SARSA update, which is very simple. From here, you have alpha, you have to set that some value. There are some heuristics to set the alpha, but there is no fixed rule to come up with the alpha. You have this discount factor gamma, and rest of the story is already given from these previous steps. So after doing this step, this update to the value of ST and AT, which is this, you sample ST and AT, and Q of ST and AT is the state action pair, state action function pair. You update this in iterative manner. After that, what you do is you set your time step t to t plus 1, which means now you have reached the state as t plus 1. So when t is t plus 1, when we will refer again as t, that means the next state, which is st plus 1, and from there the algorithm will continue. So next we talk about the terminal state. In several cases, the tasks that we actually are working on are episodic tasks. So an episodic An episodic task is a task that has some terminal state, and when you reach a terminal state, you actually exit the state. For example, in several games, think for example a maze, and your agent has to exit the maze. And when the agent basically exit the maze, that particular state, one episode basically finished. No matter where in the maze you start, whatever the first state was, you keep wandering, maybe a random walk, maybe a policy walk, whatever. You keep wandering in the maze, and whenever you exit, one episode finished. So an episode is episode finished when you reach a terminal state, and several games have their terminal state. Once you reach the terminal state, you have to restart by sampling some other state as initial state, but you leave the Q values that are already learned unchanged. So you do not initialize Q again. So you use the learned Q, but you start from step 2 to onward. So if you reach a terminal state, then go to step 2, sample an initial state at random maybe, and just follow all these steps the way down. Move it. If you do not reach the terminal state, then go to step 3, which means start from this particular state here. Start from this state and move down. Yeah. So which means if you are not in a terminal state, then next time you will sample an action AT from the state ST plus 1, and remember T has already changed to T plus 1, which means the previous action lead to a state, and that state now become an initial state, and all the algorithm starts from there. So if you reach a terminal state, one episode finished. And once an episode is finished, you start your algorithm completely. Just the initialization of Q is not happened. The rest of the algorithm restarts from the very beginning. You random sample an initial state and you move on. And this whole algorithm runs for a particular number of episodes. So there is maybe a max episodes. There may be like max iterations in several algorithms. Here the iterations are the number of episodes. So how many episodes you really want to run. And remember, each episode can be randomly different than a previous episode. So the state action sequences, which is sometimes called the episode, you start from ST, you take an action AT, you observe and reward RT plus 1, you move to ST plus 1, you take an action AT plus 1, you observe a reward RT plus 2, and so on. This is one episode until you reach some terminal state. And by the way, at the terminal state, if ST plus 1 is a terminal state, then the Q value, the state action pair value function is defined to be 0 for terminal states. So once you reach the terminal state, the episode finished, you start another episode, then you start another episode, and there is some maximum number of episodes that you have to go through. That's completely the SARSA algorithm, and it depends upon a particular policy to sample the action at ST plus 1 state. Obviously, you have sampled an action at ST, but the estimate you really want to find out the estimate Q that you really are using for the target, that is for ST plus 1, and for ST plus 1 you sample an action AT plus 1. So that is your sampled action. The whole difference of SARSA and Q learning is the sampling of this action AT plus 1. So let me describe that in my next slide. So focus on this. You have sampled an action AT plus 1 with a particular policy from the state ST plus 1. The difference between Q learning and the SARSA is, it is again exactly the same like SARSA. You initialize, you have some random state to start with. You sample an action with some policy, maybe a greedy policy, or maybe just a random sampling, uniform random sampling, where all actions are equally likely, or maybe some epsilon greedy policy, whatever. You you have some policy to sample in action AT. Then you observe the reward just like SARSA. You switch to new state just like SARSA, but you do not sample action at state t+1 by a policy. What you do is you pick the action that maximizes this function. So at st+1, you become really, really greedy. I mean, if you go back to previous slide, at state st+1, you pick the action, you sample the action. You sample the action using particular policy. But at state t+1, in Q-learning, you actually pick the action based on the completely greedy choice. And it is easy to show. One can show that this kind of action computation with greedy choice actually optimizes directly the optimal state action pair. So what you do is you pick the maximum action, the greedy action, the action that maximizes this, the greedy, at state t+1. So you do that. The rest of the story is exactly the same, just like SARSA. You have the same kind of update rule, and you set your t to t+1. If you are in the terminal state, go to step 2 and continue. If you're not in the terminal state, go to step 3 and continue. And that's the whole Q-learning algorithm. Again, I want to mention that the difference between Q-learning and SARSA is just the action sampling at st+1. So at state t+1, if you sample an action with respect to policy, you are in SARSA with respect to the policy. If you have deployed no policy at state t+1, but you pick a greedy choice, you have applied a Q-learning, which is sometimes called the off-policy learning. Yeah. So that's the SARSA and Q-learning and their comparison. In the next part of this video series, we actually will implement this Q-learning algorithm in NumPy from scratch on our map rover example that we have seen earlier in this video series. So hope to see you in the next video.